green light. Just put this somewhere to your shirt.
You want it to be closer to the...
Yeah, maybe not like all the way at the top, but yeah. And this can go in your pocket or clip on or something.
So it's already hot?
It's already hot, yeah.
Okay.
Ready to go?
Yep.
All right, let's get started for the last session of the day. So we're starting a new series now. Yifan Wang from NYU is here, and he's going to talk about two-dimensional CFTs and generalized symmetries.
All right. Am I audible? Okay. Okay. So thanks for the opportunity to present something about a subject that I love very much. That is about conformal field theory, in particular conformal field theory in two dimensions. And as you probably have noticed, conformal field theory has featured importantly in many of other speakers' presentations. And that's partially because it's a really powerful tool to study quantum field theory beyond perturbation. Okay. So here, maybe let me start giving you a very quick overview of some basics for conformal field theory. And we will go into much details in this lecture by studying conformal field theory in two dimensions. Okay. So here, just a brief overview of the basic important aspects of conformal field theory. Okay. And it's a somewhat belated kind of summary, given that you are already exposed to this subject through other presentations. So first of all, what is conformal field theory? Okay. Conformal field theory is a special kind of quantum field theory. It's a special kind of quantum field theory characterized by enhanced space-time symmetry that is known as a conformal symmetry. Okay. What is conformal symmetry? You start from the symmetry of a Euclidean quantum field theory. So for convenience, I'll be using the Euclidean language, but you can freely exchange between the Euclidean and the Lorentzian language by doing weak quotation. So Euclidean quantum field theory, I'm talking about the relativistic quantum field theory. So we have the Lorentz symmetry, the Euclidean version, and the translation. Together, that's the Poincare symmetry. And conformal symmetry is an enhancement of this to this bigger group, SO d plus 1, 1. Okay? That's known as the conformal group. So in addition to the generators that you already have in your Lorentz symmetry, these Lorentz rotations, and the translation generators, the conformal group contains, in addition, the dilatation operator, okay, which generates by this operator D. And in addition, this somewhat more mysterious special conformal generators, commonly denoted by K. And this case can be related to the generators of the translation, commonly denoted by P, okay, by composing with the so-called inversion. Okay, where the inversion transformation sends a point in the space-time to something like this. Okay, hope this is something you have seen before.
Does there need to be a minus?
Where?
On the composition of inversion.
Here? Yeah. Oh, that's just going to be our definition of the. So you're right. If I want to be completely careful, which means when I want to specify the hermiticity property of the generators. In other words, if I want to say that K is a Hermitian conjugate of P, then I need to be worried about the minus sign. But so far, it's not really important. Okay. All right. I should say that, like in any other presentation, you're welcome to interrupt me at any point if you have any questions, okay? Or if I write something incorrect on the board, which probably will happen at some point. And just a small disclaimer: the world of QFT is large. Here, I'm focusing on the case when I have the enhanced symmetry, conformal symmetry. Okay, and in addition, I will focus on the case when the theory is local. Okay, and it's unitary. And furthermore, it's compact in the sense that it has a compact spectrum, has a discrete spectrum on a compact spatial manifold. Okay, so emphasize these restrictions is not satisfied by the most general class of conformal field theories, many of which are very interesting. But just to limit our discussion, we'll focus on this particular nice class of conformal field theories. And as you probably learned from the quantum field theory class, once this kind of property is satisfied, there's a way to characterize any symmetry using Noether currents. And for the spacetime symmetry, the corresponding Noether current can all be constructed from the stress tensor. For any quantum field theory that satisfies these properties, okay, you have the stress tensor, which you can improve to be a symmetric rank 2 tensor. And furthermore, satisfying the conservation or divergence-less condition, okay, in the presence of additional conformal symmetry, the stress tensor needs to satisfy an additional condition. That is, it has to be traceless. Okay? And once you have stress tensor that satisfy these properties, you can construct Noether currents that correspond to each of the generators of the conformal group. And these Noether currents can be constructed, well, there are currents, so you have one vector index. They can be constructed from the stress tensor. The stress tensor satisfies this property is referred to as the conformal stress tensor. The Noether current can be constructed from this rank 2 tensor by contracting with a vector, okay, like this. As long as the vector satisfies the so-called conformal Killing vector equation, okay, so as long as this is satisfied, okay, you can check this current is indeed conserved using the set of conditions for the stress tensor we wrote above. Okay. And another way, here I'm being rather quick, another way to introduce conformal symmetry is to look at coordinate transformations on flat space in this particular case that transform the metric up to an overall factor. Okay. And this is the same equation that, that boils down from that condition at the infinitesimal level. Okay. So the usual killing vector equation will be corresponding to you have nothing on the right-hand side, and that will give rise to this usual Poincare group. In the presence of symmetry, as is the case with any symmetry, operators in the quantum field theory will fall into representations of that symmetry. So a powerful consequence of a quantum field theory that has conformal symmetry is that operators, there's a very efficient way to organize operators in the sense that they fall into representations, or in other words, of conformal symmetry, or in other words, conformal families. Okay? And in the unitary context, each of these conformal families will be characterized by something like the head of the family. And that's usually referred to as a primary operator. And it's characterized by some quantum numbers that keep track of the quantum numbers of this operator under a maximal commuting subalgebra of the conformal symmetry. So over here, delta is the quantum number characterized as scaling dimension, eigenvalue with respect to d, and j characterize the potential spin quantum numbers. All right, so far, seems like I just introduced you some abstract quantum field theory, some special kind of quantum field theory. Okay, so what's so special about this quantum field theory? So it turns out this kind of quantum field theory, so this is known as a CFT. Okay. The conformal field theory, in other words, CFT, shows up quite ubiquitously in various contexts of theoretical physics. Okay. So the next comment to answer where they show up. So one common place where it shows up is in the context of second-order phase transitions. Okay. That happens in nature. For example, happens in magnet and also water at a critical temperature. And in all those cases, there are interesting critical phenomena, and the physics near these critical points are governed by a quantum field theory that has this enhanced symmetry that correspond to some CFT. And secondly, related to something that Nati talked about, is that this conformal field theory can arise as fixed points of RG flows. Okay. So they're like important points in the theory space quantum field theory that govern the physics near these fixed points. And emphasize these RG flows does not need to emanate from quantum field theories themselves, but it could start from a lattice system, okay, where we have this emergent Poincare symmetry, and that's further enhanced to the conformal symmetry. And finally, as we learned from ADA CFT, this conformal field theory sometimes secretly encode dynamics of quantum gravity. Okay. So given this kind of motivation, you probably already convinced that conformal field theory is an important subject to study. But let me just make a few remarks to make this even more explicit. So an important fact of nature is that physical systems are classified according to what's known as universality classes. In the sense that very different systems that has very different definition at short distance exhibit the same behavior at long distance. And in particular, they may exhibit the same critical exponents at their second order phase transitions. Okay, even though they are very different systems. And second of all, conformal field theory is really one of the very important tools that we can use to attack non-perturbative quantum field theory. Okay. And finally, linked to this point, it opens a window, opens a potential bridge to understand quantum gravity using field theory techniques. Okay. So that's the motivation. But how in practice can we use conformal field theory? How in practice can we study conformal field theory? How to solve a conformal field theory? So as Nati emphasized in one of his lectures, okay, the traditional approach to quantum field theory based on Lagrangian suffers from ambiguities in the sense that the naive degrees freedom you see from a given Lagrangian description for quantum field theory could be misleading because there could be multiple different Lagrangian descriptions of the same underlying dynamics. So a better approach to describe a quantum field theory is using the operator algebra language. Okay, so it does not suffer from the same ambiguities from the Lagrangian approach. But in general, this is a very hard it's a very hard strategy to pursue for generic quantum field theory. But things are under much better control in conformal field theory, where there is an axiomatic and efficient approach, as we'll see in concrete examples, to solve a conformal field theory via the so-called conformal bootstrap method. Okay, so there are many successful stories about conformal bootstrap from recent years. I will not have time to review that, but we'll see some example of this idea in the concept of two-dimensional conformal field theory. Okay, so given these broad motivations, just want to convince you that conformal field theory is a very good place to study quantum field theory at an unperturbative level. And in connection to the theme of the topics discussed by other lecturers, it also be a perfect place to study general features of generalized symmetries without relying on having a perturbative description. Okay. All right. So I believe later in the school, David Simon-Stephan will talk about conformal field theory, probably a different way. Okay. But I think he will focus on higher dimension. But some of the things I will cover in this lecture will have natural generalization in higher dimension as well. So I hope what you learn from here will be useful for for understanding his lectures too. Okay. So from now on, I will focus on conformal field theory in 2 dimension. Okay. For most of these talks, I'll be using interchangeably between these 2 languages. Okay, it's 1 + 1d versus d = 2. And for conformal field theory in 2 dimensions, something very special happens. Okay, the special thing that happens is that the conformal symmetry. Okay, when you never have the conformal symmetry, in 2 dimension, subject to these conditions. Okay, in the quantum field theory, that symmetry gets automatically enhanced to an infinite dimensional spacetime symmetry. And the way to see that can be facilitated by using this parametrization of the spacetime in terms of complex coordinates z and its conjugate. Okay, so these are coordinates on R2. Okay, the spacetime for our conformal field theory. So what is this enhanced symmetry? So we start from the conformal symmetry in d = 2. As you can read out from this general formula, it's going to be SO3, 1. Again, this is the Euclidean version of the conformal symmetry. Okay. At the level of a Lie algebra, this is equivalent to SL2C. Okay. And this is nothing but the group of, well, the algebra of Mobius transformations that you probably learned from a complex analysis class. And it's very simple. If you parameterize these transformations in terms of these complex coordinates, it simply acts by these fractional linear transformations in the following way. Okay? Where A, B, C, D are complex numbers subject to the constraint that AD minus BC is equal to 1. Okay? So this is just about the global conformal symmetry. So this is also known as the global conformal symmetry in 2 dimensions. But as I said, as we'll see, this will get enhanced to a much larger, actually infinite dimensional symmetry that's known as the Virasoro symmetry. And you have 2 copies of them. I'll denote it by Virasoro and Virasoro bar. Okay? We'll discuss this symmetry in more detail shortly. But here I just want to give you a picture of what's going to happen. And here, an exercise for you is to see that the symmetry gets enhanced by analyzing solution to the conformal Killing vector equation. So an exercise for you here is to show that the conformal Killing vector equation in 2 dimensions have a bigger space of solutions compared to the bigger than 2 dimensions. Okay? And the solutions can be characterized by 2 functions of z and z bar, where one of them is holomorphic and the other is anti-holomorphic. Okay? And this is why you have an infinite dimensional symmetry without going into the detail of the Virasoro algebra for the moment. Okay? And we'll introduce this shorthand to suppress the index, the vector index on these killing vectors as follows. So here, I already mentioned that the fact that you have this enhanced conformal symmetry leads to a drastic simplification in the organization of operators in your theory. Okay? For example, given any operator, is if you hit derivative on that operator, all those operators will live in the same conformal family. Okay? So each conformal family would contain an infinite tower of operators. That's why it leads to this drastic simplification in the dynamics of the theory. Here, we have a further enhancement of symmetry, okay, from the conformal symmetry to even infinite dimensional symmetry. So you would expect an even more drastic simplification in the corresponding operator spectrum, okay, and as you'll see, also for the corresponding algebra between these operators. And this turns out would also amplify the power of conformal bootstrap. It will lead to very very concrete, powerful results in d equal to 2 compared to higher dimensions. So at this point, if you have heard about two-dimensional conformal field theory before, but you haven't studied it in much detail, maybe there's a couple myths or beliefs that I want to clarify. Okay. The first common belief or common myth is that 2D CFTs are solved. Okay. They're essentially solvable, and it has been solved. Okay. This is clearly false. Otherwise, I wouldn't be giving this lecture. It's something you can just read from the textbook. Okay. The second, more non-trivial belief is that the 2D CFTs are rational. Okay. We'll get into the precise definition of rational, but roughly speaking, what rational means is that the symmetry, the conformal symmetry, the enhanced infinite dimensional conformal symmetry, okay, is so powerful such that the entire infinite dimensional operator spectrum actually truncates into a finite number of conformal families. Okay, that's the notion of rational. And for the expert, the notion of rational would depend on, crucially, on possible further extension of the infinite dimensional symmetry that happens when you have additional conserved current and so on. Okay, but this is a rough idea. And this is some belief that's even shared by experts in this field. And this is also false. And this is not hard to see if you listen to Nati's lecture carefully, because Nati has already given an example where this condition is, so this condition here, I should write it, so otherwise there's nothing to contradict with. And finite number of conformal families, also more precisely known as conformal blocks. Okay. Because there are counterexamples, and the counterexample, to look for those counterexamples, you don't have to try very hard, already the C equal to 1 compact boson at general R is irrational. Okay, it does not have a finite number of operators. In particular, for general radius R, the symmetry of the theory is just Virasoro squared. Okay. Well, there's additional U1, but even if you include the additional symmetries, you see that there are infinite number of conformal families that are labeled by the momentum and the winding numbers, precisely. Okay.
Just to be clear, some 2D CFTs are rational.
Yeah. Oh, yeah. That's right. So, okay. Yeah. All right. And if you're more sophisticated, if you like geometry, and there are other examples which that falsifies this claim, that includes supersymmetric sigma model on Calabi-Yau manifolds. In which case you have the marginal parameters. These theories are typically parameterized by a continuous family. That parameters come from geometric modulus of this Calabi-Yau manifold. And for generic point on this conformal manifold, parameterized by this geometric moduli, the theory is not rational. Okay. But maybe you will still complain. Okay. All the examples I gave you so far, even though they are not rational at generic point, because all these theories come with a family, they are not rational at generic point. But maybe you'll complain because they're all they could be connected to rational points by marginal deformations. Okay. So a more sophisticated claim will be that all 2D CFTs are almost rational. So I'm being kind of purposely vague here a bit about the notion of almost. But intuitively, then it just means that the claim here is roughly speaking that any 2D conformal field theory is near some rational conformal field theory. Okay? For example, if it can be obtained by a small marginal deformation from a rational point. And this is very hard to, this is much harder to falsify, but it's probably false thanks to a recent nice paper that construct a very convincing example of a theory that's irrational and doesn't seem to be close to any rational conformal field theory. This is the paper from Altunis and Behan from 2023. Okay, so the upshot of presenting this myth and and falsifying, giving you telling you that they're actually false, is the punchline here is that the space of 2D CFT is much uncharted. Okay, and in particular, as you'll see, this is also even for the examples that are solved or rational. Even for the theory that we think they are solved and rational, there are still a lot of stuff to be understood that involve, for example, the possible symmetries in those theories. In particular, we saw from Nati's talk that even the Sigtuan boson, okay, which is solved, okay, contains a rich, rich information about symmetries, and the symmetries have subtle features that are seen in more complicated examples, such as anomalies. Okay, question? Yes.
Do you think we can say that almost all 2D CFTs are almost rational?
There are too many adjectives, so I wouldn't want to commit on recording. Okay, but I'm happy to talk about it, my personal perspective later. Yeah. Okay. All right, so that's some motivation, and now let me present the rough plan, subject to change, especially after Nati's lecture, for the subsequent lectures that I will be given. Okay. So first of all, I'll discuss Virasoro symmetry in a little more detail, okay, which I introduced briefly over there. And I'll talk about the structures, axiomatic structures of operator algebra in two-dimensional CFT. And then I will talk about something very special to two-dimension. It's a very powerful tool to study 2D CFT, which is the torus partition function, and the very powerful constraint coming from modular invariance. We'll be able to say a lot about 2D CFT just using this property. And then I'll talk about orbifolds, and in particular, orbifolds with respect to discrete invertible symmetries. Okay, this will make connection to what Nati talked about earlier today. And then I'll generalize the group symmetries, invertible symmetries, to general symmetries, which are characterized by topological defects. Okay, hopefully this notion, thanks to Sakura and Nati's talk, have really penetrated. Okay. And then I'll talk about generalizations of orbifolds if I have time, generalizations of the orbifolds in this context using topological defects that leads to a generalized notion of gauging. And if I have more time, I'll talk about other interesting aspects of 2D conformal field theory, including boundary conditions and conformal defects. And throughout the talk, I'll try to give examples. And the examples, for those of you who anticipated, the examples I'll be given, okay, are all contained in these two classes. Okay. Unfortunately, I won't have time to talk about this last, although it's very interesting by itself. Okay. All right. So let's jump right in. So we'll start by discussing the symmetry. Okay, and this theme of the workshop, theme of the school is aspect of symmetry. In my lectures, there are two heroes. One is conformal symmetry. In particular, its generalization. There's further enhancement in two dimension, the Virasoro symmetry, and the other is the generalized global symmetry. And in the first lecture, we'll mostly focus on the first hero. Okay, that is Virasoro symmetry and its consequences. Okay. So as I already mentioned, a CFT, a hallmark of a CFT is that the presence of a stress tensor that is traceless, in addition to being conserved and being symmetric. And in terms of the coordinates that we introduced, that's most convenient in 2 dimension. There's a question? Yes.
Just a little bigger.
Oh, sorry. Is it better?
Yes.
Okay. In 2 dimensions, in the set of coordinates that we introduced, that's most convenient. This complex coordinates z and z bar. This boils down to the condition that this component of the stress tensor is 0. Okay, this is coming from the traceless condition. And the conservation condition tells us that the holomorphic component, the purely holomorphic component of the stress tensor, is a holomorphic function of the coordinate. And similarly, the purely anti-holomorphic component of the stress tensor is anti-holomorphic function. Okay. And the conformal Killing vectors, so which I denote abbreviatedly as CKV, okay, are holomorphic function of z, and epsilon bar as anti-holomorphic function as a function of z bar. And this leads to finite. There's a finite version for any transformation, okay, that characterized by a CKV. As usual, you can integrate this infinitesimal transformation and give rise to a finite transformation. And it's not hard to convince you that the finite transformation correspond to this infinitesimal ones will be general holomorphic change of coordinates and anti-holomorphic change of coordinates for z bar. And as the case for anything in quantum field theory associated with this symmetry, there are corresponding charges which will tell us how the symmetry acts on local operators. And in these cases, the charges, which I'll refer to as conformal charges, okay, they are given by modes of these holomorphic objects, T of z, and this anti-holomorphic objects, T bar of z bar, in the following way. Okay. Which you can thought about as usual Noether charges associated with the current, where you take epsilon to be generated by a basis that corresponds to monomials in Z. Okay, remember that. I think I just erased that. From this rank 2 tensor, you can construct the corresponding Noether current, which are vectors. The way you construct Noether currents to contract this rank 2 tensors with the conformal Killing vectors. Okay, and to construct the individual charges, you need to choose a basis for these conformal Killing vectors. And here, the convenient choice is chosen to be these monomials because they are holomorphic functions. Okay, so you have infinite family, so all these n are integers. And the equivalent to think about this is that for these holomorphic operators, you can do a Laurent expansion, and the coefficient of the Laurent expansion are these conformal charges, okay, which will act on local operators. So it's just the equivalent way of writing the above integral. Okay. And this, as we'll see, these conformal charges are also known, well, from what we said, this will be the generators of this enhanced conformal symmetry. And for that reason, they're also known as Virasoro generators. Okay. Of course, just writing down the charges for a symmetry doesn't say much apart from how many charges you have. The important information about symmetry will be captured by commutation relation between the charges. Okay? And to derive the commutation relation between these charges, the L between themselves and the L bar between themselves, and potentially between L and L bar, you need to understand what happens when the stress tensor collide with one another. Okay? Because you were taking commutators of this integral of the stress tensor. And this integral are over a contour that's surrounding the origin in these equations. Okay? So when you take the commutator, necessarily there are points where they collide. So it's important to understand what happens when the stress tensor collide. To calculate the commutator. Okay? And this is coming from the notion of OPE, okay, known as operator product expansion. This is too small. Sorry. Okay, but before writing down the explicit form of this OPE, let me introduce some general general concept between this powerful machinery that's available in two-dimensional conformal field theory. Okay, this you can do in general quantum field theory, but it becomes extremely powerful in conformal field theories, and even more powerful in two-dimensional conformal field theory. Okay. So before introducing that, I introduce an important concept in conformal field theory, which will help us to understand OPE. Okay, that is the state operator correspondence. Okay, which roughly speaking says that the space of operators, okay, which I denote this set of O, okay, will be equivalent to the Hilbert space on S1. Okay? So we'll be considering quantizing the two-dimensional quantum field theory on a compact space. The only possibility you can have is a circle or a collection of circles. So the basic building blocks will be the Hilbert space on S1. So where is this S1? Okay. So we can consider this to be our plane. Okay. And then we can take the S1 to be a circle around the origin. Okay? We're free to choose where our origin is. Suppose this is our origin. Okay. So how does the space operator correspondence goes? The way it goes is that you can construct the state on this S1. Okay, so this is where this Hilbert space lives. Okay. You can construct on this S1 by doing Euclidean path integral over this region. And this one way of the relation comes in is when you insert, you can do the Euclidean path integral with the option of inserting a local operator at the origin. So for any such insertion, okay, running the Euclidean path integral will generate a state in the Hilbert space on S1. And this picture is also known as radial quantization. Because the Euclidean path integral, okay, on this disk implements the time translation in the radial direction. So it corresponds to taking the Hamiltonian that implements the time revolution according to the dilatation operator, okay, which, as we'll see, will be related to the Virasoro generators L0 and L0 bar in this way. So I explained to you one way of this correspondence, namely starting from a local operator, how to get the corresponding state. Okay, so how do I go backwards? So given a state in the Hilbert space, okay, as you can imagine, we can use this dilatation operator to evolve the state backwards to the origin and get the operator. You may object at this point that at what stage have I used the conformal symmetry? Okay. Instead of talking about this evolution with respect to the dilatation operator, I can do everything using the Euclidean path integral. I can do this backward time evolution by doing the Euclidean path integral backwards. Okay, something that I think Juan also mentioned in a different context. What buys us, what the subtlety is that in principle, in general, this backward evolution is very messy, and this limit may not exist. Okay, and with conformal symmetry, it helps us in the following sense. So first of all, with the conformal symmetry, okay, and as we'll argue later, this dilatation operator is Hermitian, and it can be diagonalized on the Hilbert space, which means states in the Hilbert space will be graded by their scaling dimensions, quantum eigenvalues with respect to d. Okay, and the evolution, the backward evolution, will introduce scaling factors that depend on the scaling dimension of a corresponding state. So in general, there will be a huge scaling factor as you evolve backwards. Okay, and if you have a state that is an infinite sum of the following type, okay, where each state is eigenstate with respect to the dilatation operator, as you evolve backward, okay, in time, suppose the amount of time in the radial direction here is parameterized by lambda, okay, you will pick up a phase that's proportional to lambda times delta I. Okay, so if this is like an infinite linear combination of dilatation eigenstates with arbitrarily high delta, then this limit does not exist because this scaling factor will blow up. Okay, but if you truncate this sum, limit to a finite, the sum of finite number of dilatation eigenstates, which you can do in the case when you have conformal symmetry or scaling symmetry in this case, then this limit is so emphasize here, truncate. Then you can safely evolve backward radially to get a local operator at the origin. Okay, so this is where conformal symmetry is important.
Why you can truncate just when you have?
So this way, this allows you to associate local operators to a dense subset of the Hilbert space. In other words, for any finite sequence of states in the Hilbert space labeled by the scaling dimensions, you can associate with the local operator, and it's dense. So this is the precise sense of this operator state correspondence.
But where the conformal symmetry?
Conformal symmetry allows you to grade states by scaling dimension. It's a preserved. It's on this quantum number. Okay. Okay. Yes. That's right. That's right. So the correspondence between local operator insertions and states on this circle just relies on using the Euclidean path integral. So you always have that map. Yes. Well, if there are different operators, yes. Generically, I mean, if in special quantum field theory, there may be. Yeah. Okay.
There's another question.
Yes.
Okay. So, what is the difference between this truncation that you're doing here and the truncation that you said isn't possible because you have some?
Where?
This truncate, you're saying that you can do a truncation here.
Yeah.
Like you have a finite number of conformal ways.
Yeah. So for each state, when I run this argument to show that there's a local operator corresponding to it, by backward evolving, I'm only considering a finite sum of dilatation eigenstates.
Okay.
Yes.
And states can be made up of finite numbers of.
But this will give me a dense.
Even though
That's right, because I can, yeah, that's right, yes. Okay?
Sorry, do we need conformal symmetry to have this?
Scaling symmetry. Here, I only need a scaling symmetry, yes. Okay? But it's a very non-trivial fact that, so I erased that. When you have scaling symmetry and your theory is unitary and local, okay, it's a very deep fact that in special dimension has been proven that the theory will have enhanced conformal symmetry. Okay? It's not proven in general, and there are small caveats, but it's generally expected to be the case. All right. And the useful picture, another useful picture to think about the radial quantization can be obtained by implementing a Weyl transformation. So this is something let me say it over here. So the conformal field theory, in addition to having conformal symmetry, also have a Weyl symmetry, which you can derive as a consequence of having the traceless stress tensor. And the Weyl symmetry is a statement that, so this is a consequence of the traceless stress tensor, and this is also true in general dimensions. It's a statement that observables on the space-time manifold, a pair of space-time manifolds whose metric are related by rescaling by a scalar factor are identified. Okay? There are a precise relation relating these correlation functions, for example. So it means that when you have space-time manifolds related in this way, this is known as the Weyl factor. Okay? There's a precise relation between the correlation functions, which I'll not write here to save time. That's a consequence of this Weyl symmetry. Okay? Emphasize is different from conformal symmetry in the sense that we're not keeping the metric fixed. Okay? Or said differently, you can think about conformal symmetry as a combination of the coordinate transformation that's whose infinitesimal version is epsilon, whose finite version is f. Okay? Conformal symmetry is a combination of this diffeomorphism transformation, or coordinate transformation, combined with Weyl symmetry, such that the metric stays the same. Okay? By doing a Weyl transformation, you can see that the plane will be equivalent to a cylinder. Okay? In this case, the metric, you can write the metric on the plane as follows. Okay? And this can be related to the metric on the cylinder. So I introduce these coordinates. Tau, that's the time direction on the cylinder. And the circle direction, I'll call it sigma. Okay? I introduce another complex coordinates, which I call W, which is tau. So my convention is that sigma plus I tau. Okay? So sigma is subject to the periodicity condition. And then this is related to the metric. So this is the metric on the plane. It's related to the metric on the cylinder, which is simply dw bar, okay? Because another complex, another flat metric, okay? Just with the identification. They're related by a Weyl factor. The Weyl factor is nothing but e to the 2 tau. Okay? That's the corresponding omega squared over here. And then in this picture, okay, this is at tau. This is tau goes to minus infinity. This is tau goes to plus infinity. Okay, and you can keep track of the blue circle as a circle over here. Okay, once you do this Weyl transformation, you see the local operator will map into a state that's inserted at the time past infinity. Okay, and that's corresponding state. We'll call it O. Okay, and the precise relation between that state and the local operator can be thought of as follows. Okay, where this should be thought of as the vacuum state, which in this picture correspond to inserting nothing and doing the Euclidean path integral. Okay, and the insertion at the origin of the local operator will create this non-trivial state, which I label as follows. So the reason I introduced this cylinder picture, okay, is because it makes manifest of a Lorentzian structure which will be needed in order to kind of understand the Hermitian structure which underpins the unitarity of the theory. So we need to. So basically, what we want to understand is what Hermitian conjugate means. Okay, in the Euclidean conformal field theory that we have been describing. And the way you do that is to go from the Lorentzian description, where the Hermitian conjugation is manifest, and then you port that into the Euclidean description by implementing the Weyl rotation. So what is the Hermitian structure over here? Okay, and this will start from the this structure on the cylinder, okay, where there's a natural direction of time. Okay, so for the moment, let's think about this as a Lorentzian cylinder, where this direction is time. Okay, it's Lorentzian time, and the operators on the cylinder in the Lorentzian signature. I'll use the subscript L to emphasize it in the Lorentzian signature. It's inserted at some position, which I call T and sigma. T will be the Lorentzian time. And to go back to the Euclidean description, you need to do a Weyl rotation. In this way. Okay? Where tau is the Euclidean time. In the Lorentzian theory, we all know that if you have a real operator, its Hermitian conjugate is very simple. It just says the Hermitian conjugate is itself. Okay? If you have a complex operator, like a linear combinations of real operators with i's, then the operator will also receive a complex conjugation on top of this simple relation. And note that this is in particular consistent with the Heisenberg picture, where you can strip off the time and spatial dependence using the Hamiltonian and translation operator as follows. Okay, suppose this is a Hamiltonian that tells you how to evolve the theory in this Lorentzian time direction. And P is a translation that tells you how to translate the operator along this compact circle, sigma direction. Okay, all the positions of the i's and the minus signs are important, but you can see using the fact that H and P are Hermitian. Okay, this relation is consistent. I'm undertaking Hermitian conjugate of right-hand side. Okay. Now, implementing the Weyl rotation using this relation and the definition that the Euclidean operator after the Weyl rotation at the Euclidean time tau and sigma is related to the Lorentzian one by the rotation of the coordinates. Okay, and using this Heisenberg representation, okay, to relate to the Lorentzian operator inserted at the origin, the presence of the I here means that this relation no longer holds for the Euclidean operator. Instead, something very simple happens as you take the Hermitian conjugate. That is, the Euclidean time gets reflected. Okay, nothing more. So the punchline here is that the Hermitian structure, the Hermitian conjugation in the Euclidean signature involves, on top of a complex conjugation in case the operator is complex, on top of that, a reflection in time. Okay. So this is Euclidean Hermitian conjugate reflection in time. Okay? And using the relation between the cylinder and the plane by a Weyl transformation, and the fact that conformal symmetry is a combination of the change of coordinates and the Weyl transformation, okay, one can deduce that for the operator on the plane, okay, there's a similar conjugation, Hermitian conjugation. So on the plane, so after a Weyl transformation, on the plane, the Hermitian conjugation will take the following form. Okay. Note the funny change in funny reflection. So this is another reflection on the coordinates of where the operators are inserted. But it's nothing but the consequence of reflecting tau and using how W and Z are related, which I didn't write, which is simply this way, but something that you may have already guessed. Okay. So using that simple relation between Z and tau and sigma, and this relation, you can already see that Hermitian conjugation involves reflection on the coordinates in this way. Okay, it's a reflection in the sense that it's a Z2 operation, but more precisely on the plane, it's an inversion. Okay. It's the two-dimensional version of the inversion transformation that I talked about in the beginning, that involving sending x to x over x squared. Okay, this is the two-dimensional version. This is not a complete thing. Okay, that's why I left some space. Okay, so if you work out it carefully, keeping track of how operators transform under a Weyl transformation, there will be some overall factors. And in the case of scalar operators, so operators that carry no spin, so the quantum number with respect to the spin is 0, you just have a non-trivial scaling dimension. Then this prefactor is a function of Z that depending on the scaling dimension. Okay, and this conjugation is known as the BPZ conjugation. Okay, just to distinguish with a naive Hermitian conjugation, you may want to define for operators on the plane. And this is the conjugation that remembers the Hermitian and corresponding unitarity structure underlies this quantum field theory, this conformal field theory in this case. And as an exercise for you, okay, try to work out the BPZ conjugation for spinning operators. Okay. In particular, here I'll just write one particular example. Is that if you take the stress tensor, okay, which has spin 2, implement the procedure outlined over here. Okay, study how the stress tensor transform in the Lorentzian signature on the Lorentzian cylinder under Hermitian conjugation. Do the recoltation and then do the Weyl transformation. You should find on the plane under BPZ conjugation the stress tensor transform in the following way. Okay. All right. So with that, we can finally talk about some general aspect of this OPE, operator product expansion. Which will make use of the Hermitian structure that we just discussed. Well, more precisely, just the fact that we will have the underlying Hilbert space that's manifest in the cylinder picture. Okay, so what is operator product expansion? It's a very general idea that when you bring two operators close to one another, you can expand it into some elementary building blocks. Okay, so there's some, in a sense, there's a preferred set of basic operators. And when you bring two operators together, you can expand into these basic blocks. And this allows you to reduce the general correlation functions into correlation functions that involve a fewer number of insertions. Okay, so this will be a very kind of a powerful tool to systematically analyze correlation functions in a conformal field theory. So this is something that you can use in quantum field theory as well, but it's most powerful in conformal field theory for the reason that I'll explain shortly. So the picture you should have in mind is that you're on the plane, okay, and you have a bunch of operator insertions, okay, and in particular, let's pick out two of the insertions over here and here, okay, label them by OI and OJ, okay, and assume that there's a circle that encloses these two okay. Assume there's a circle that encloses two operators and nothing else. Okay. And you ask, can you replace these two operator insertions by a sum of single operator insertions? Okay, that's the notion of OPE. How do we do that? Okay, so what we want to argue is something looks like this. Okay? So suppose the operator I is inserted at position Z, operator J is inserted at origin. What we want to see is some relation that looks like this. Okay. Where the C will be some function that depend on Z, okay, but it will be some it will be some function that depend on Z, okay, and also the operator you started with. Okay? If we can achieve a relation like this, we can recursively reduce higher point functions to lower point functions. Okay? And as you probably would imagine, that the correlation functions of lower points are much simpler than correlation functions involving higher points. So this will be a very efficient way to study correlation functions in the conformal field theory. So how do we derive such a relation? Okay. The way we derive such a relation is to think about this using the operator state correspondence. Okay? In other words, we think about the corresponding state created by these two operator insertions in the Hilbert space that's defined on this circle S1. Okay? And from the general discussion that I gave over there, the state that's created by these operator insertions can be characterized as follows, okay, by these guys acting on the vacuum that correspond to the state created in this superspace with no operator insertions at all. And the equation we want to show look like something of the following form. Okay, so this way of writing the equation makes this relation almost trivial from what we just discussed. That is because this, by construction, the psi will be a state inside this superspace. And we just said that there's an operator state correspondence, okay, that says that any state, at least a dense subset of states in the superspace, can be constructed by linear combinations of states created by local operator insertions at the origin. Okay? And that's precisely what leads to the second equality. Okay? Yes. No, so that's what I'm come to. Yeah. Okay. But you may still complain, like, is this a formal sum? This is going to be infinite sum, okay? But then you complain whether this sum converge, okay? So the statement is that this is a convergent. It's a convergent sum in the sense that I'll define now, okay? It's a convergent sum in the sense that in any correlation functions, okay, it's a convergent sum that you can see just from the following fact by taking the inner product of the state psi and its Hermitian conjugate. Okay? And this is where we use the BPZ conjugation, because this correlation function will be given by, on the vacuum, OJ is Hermitian conjugate, and OI is Hermitian conjugate. Will be given by a correlation function of this type. Okay, this is what this bracket is. Okay, if this state is normalizable, then this sum must be convergent. Okay, this is the usual fact about states in the Hilbert space. If the state is normalizable, then this sum is convergent. And why is this? Why this being normalizable means that the right-hand side needs to be something finite. Okay? And the reason it's finite is because this operator, after taking the BPZ conjugation, will be inserted at a different location where z is mapped to 1 over z. And here, let me be precise here, I'm taking this circle to be located at the unit distance from the origin. Okay? And by that choice, okay, z is sent to 1 over z bar. By that choice, all the operator insertions in these correlation functions are away from one another. Okay? That's the reason there's no singularity in this correlation function. The singularity will come in when some operators collide, but all the insertions will be away from one another. Okay? And this will be finite. Okay? And thus convergent, OPE. And the consequence of that is the following powerful operator identity that you can insert in any correlation functions. And in terms of this picture, concretely, you have a bunch of operator insertions, O1 all the way to ON, okay, schematically, together with these operators, which we want to take the OPE between. This complicated correlation function that involve n plus 2 insertions can be reduced to correlation functions involving n plus 1 insertions using the operator equation that we just derived. Sum over ijk, and that has the z dependence. Okay. All right, so we're now finally coming back to this the LP of the stress tensor, and to answer the question about what is the Virasoro algebra generated by commutation relation between this modes Ln and Ln bar. There's a question?
Yeah, is the OP the associativity of this fact as well?
Come again?
Yeah, is the associativity of the OP also follows from this normalizable state?
That will come from that doesn't come from here, but we'll comment on it later. That's a consequence of locality. Yeah. Yeah, we'll come to associativity. But the fact that you can do successive OPE, okay, and obtain expansions that are convergent will be a consequence of the similar argument over here. Okay. All right. So how do we determine the Virasoro algebra? Okay. So we look at the TT OPE, namely the OPE of the stress energy tensor that generates the Virasoro symmetry. This OPE is given by this stress tensor as follows. The stress tensors, okay, as always, the stress tensors in d dimensions have dimension d. Okay, in 2 dimensions, dimension 2. Okay, so without doing any calculation, you can also already imagine what is the ansatz of the right-hand side by doing dimension analysis, and also remember that the left-hand side is purely holomorphic object. Okay. So the right-hand side will be something. After doing analysis, you can realize that the left-hand side are the following structures that can show up. Okay, this is dimension 4. This has 2 plus 2 dimension 4, and this is 3 plus 1. This is dimension 4. And then all the other terms are going to be regular in the limit that z goes to w. Okay, so what I've used the dimension analysis. I've used the fact that everything on the right-hand side has to be holomorphic in z and w. I've also used the overall translation symmetry, so everything has to depend on z and w together. Okay, the z dependence. Okay, And I've also used the fact that no other operators should appear in the TTOP. That is necessary to ensure the closure of the conformal symmetry algebra. Okay? So if you have other holomorphic operators shown on the right-hand side, what that means is that when you implement consecutive conformal symmetry, some other symmetry could be generated. Okay? And that's not possible from the conformal algebra. Okay? So with those kind of information, you can already deduce the form of the right-hand side. Okay? And this too, again, is going to be fixed just by studying the global conformal algebra. Okay. Okay. And the C here is something that you can just you can write that's consistent with the condition that I mentioned, and this is known as the conformal center charge. And it's one piece of important information about 2D CFTs, and there are generalizations of this notion in higher dimensions. So after knowing the OPE between the stress tensors, then you can go back to the form.
I found this on the web.
Wait. I thought I turned off Siri, but somehow.
It's actually a good reminder also that there are 2 minutes left.
Oh, there are only 2 minutes. Okay. All right, so then I'll leave this exercise for you. That is to look at, from this OPE, derive the commutation relation between the Virasoro generators. Okay. And this is the commutation relation that defines the Virasoro algebra with center charge C. And there's a corresponding version for the anti-holomorphic part with potentially a different conformal center charge that defines the anti-holomorphic part of the Virasoro symmetry, which denote as follows, potentially with a different center C bar. And you can also argue from similar reasoning that the commutator between L and L bar has to be 0. Okay? So this commutation relation together, they furnish this enhanced symmetry that I mentioned in the beginning that's special in two-dimensional conformal field theories. I have 1 more minute. Okay?
Yes.
Okay. Okay, so maybe I'll use this 1 minute to, I think I'm covering like half of what I intended to. Maybe I use this special minute to gauge, like how many of you have seen most of these discussions before? Oh, good, okay. So I will change my strategy next time drastically. I will only list the facts without explaining. And get to the more non-trivial part that involves the additional hero of my lectures, the generalized global symmetries. Okay, yeah, as always, if there are any questions, feel free to interrupt when I list these facts, and also ask me afterwards. And I'll be around, so if you have other questions, you're welcome to ask too. All right, thank you. Wow.
How do you know that they are dense?
Sorry? So let's see. So how do you I don't think I have a rigorous argument, but it's like you're taking. But this, I think, is a general fact of Hilbert space. Because you're taking sequences of. There's a limit procedure. Yeah, and you're taking the completion. Yeah, right.
I think this is
So that's right. That's right. I want to say the hubris will be the completion of these linear combinations, where each linear combination is a finite sum of the Latissian eigenstates, and the hubris space is going to be the completion of that. And by that construction, this will be dense. But that's kind of an abstract argument. But I think you can argue it in other way by starting from a state that's normalizable, and prove that it can be written in a way that's epsilon close for arbitrary small epsilon to a finite linear combination. There's some epsilon type argument.
So I think there's a factor missing there. I think it should be MQ.
Yes, yes. That's embarrassing. Yes. Yes, yes, yes. Otherwise, the conformal symmetry algebra will be modified. Yes, yes.
Here, when you introduce a state operator correspondence, you said
Yes.
that this sum is okay.
So when I try to argue it backwards, like given a state, there's corresponding local operator. I need to use the fact that I can truncate the sum to do this backward evolution properly. Because the backward evolution will introduce this phase factor, depending on the dimension, this scaling factor, depending on the dimension of the operator. And if it's infinite sum, infinite means that the scaling dimension can be arbitrarily high. This factor blow up infinitely. So this limit is no longer well defined.
And you don't have minus n because you're doing like a backward? Or?
That's right, because it's backwards, yes.
And how is consistent with the fact that you said that this sum can also be infinite for OPE? When you expand one operator near another,
Yes, yes.
you said that this sum can in principle be infinite.
This sum is infinite, yes.
So is it consistent with? Is it consistent with this?
No, because this it is consistent. Yes. No. So this is what I was answering to the other question. So normalizable states are not necessarily written as a finite sum. Can be written in terms of infinite sum. Okay.
Okay.
But the coefficient, these z factors are crucial. You need to have the correct z factors. Okay.
Okay.
Yeah, but the finite sums are dense. Okay.
And this operator psi will also be.
So you can think about this as a limit. This as a limit of those guys. Yes. Yeah. Those psi is also normalizable. This psi is normalizable from the argument I just gave over here. Yeah.
Sorry, is that factor?
Which one?
Did you write? Or is it m times m squared?
No, it's m times m squared minus 1.
Yeah, sorry, so I rubbed it out.
Yeah. For m equal to 0 and plus minus 1 has to be 0. That's right, the global conformal symmetry. Yes. Yeah.
Yeah.
Worried when you said you would stop explaining things. So
Yeah. I will. Yeah. That's a very good suggestion. Yes. I will upload it instead of. Yeah.
are you following any text, or is it your?
I think I partly recycled my previous lecture notes. Yeah. But yeah, I will upload this. Yeah, it's handwritten, but I'll make it readable and pick out.
So when you're talking about normalizability of the state, if you are working in
Yeah.
Lorentzian signature,
Yeah.
you also have to worry about the light cone singularities, right? Like if the operator should not be separated by and should not lie on the same light cone.
Yes, but there I'm already in the Euclidean signature.
No, I'm asking like if we have to do it.
Yeah. That's right. Yeah. If they are on the light cone, then there's a light cone singularity.
That's right.
Yeah. Yeah.
I missed the part here.
Yeah.
Explain all CFTs are. When you explain why it is not true that all CFTs are almost rational, like what is.
Oh, there's a concrete construction that showed up in this recent paper where they construct one example where it's clear that the conformal dimension. So one feature of the rational theories is that their conformal dimensions are rational numbers. This is necessary in order to have a finite number of conformal families.
By rational, you mean rational with respect to the Virasoro algebra?
Or even a larger, yeah. So in all those cases, it's necessary for the scaling dimensions to be rational numbers. And in this recent paper, they constructed the concrete examples which are explicitly the conformal dimension are not rational numbers. Yeah.
mean like almost?
Almost means that if it's can be related to a rational conformal field theory by like a small deformation, for example, a marginal deformation.
And then in that construction, it's not related.
Yeah, that's right. That's right. That's right. Yeah. So these are the kind of conformal field theory that people refer to as